Alright, so today we're going to talk about derivatives of parametric equations. I want to try to motivate this with an example. Let's say we have some sort of building. This is going to be my coordinate axis as well, so if you want to think about this as xy. And let's say that here the height of the building is 100 feet. And let's say a projectile is thrown from here at an initial velocity, horizontal velocity of say 100 feet per second. Then we know that the object will draw a parabola, and the equations would be given by in the x coordinate, the velocity that depends on t is going to be constant at 100 feet per second times time in seconds, which is going to give us the distance, the position from the origin at times equal t to be 100 times t in feet. All right, and so now the y is a quadratic relation that is of the form minus 16 or negative 16 t squared plus 100, which is going to be the 100 initial height. Initial velocity in y is 0 because it's being thrown horizontally, and then we have the contribution to the position given by the gravity and the time squared. So that's going to be the height at any given time t. Alright, so that's going to draw a parabola. I already drew it, gave you an idea what it looks like. And what we're going to be interested in doing now is taking derivatives. So if I were to consider x prime, that's going to be just 100. And the units, this is in feet, this is going to be given in feet per second. And that's going to be what we know as the horizontal component of the velocity vector. Now, if I take the derivative of the y coordinate, that will give me the, well, firstly, let's compute it. So negative 32t. And that's also going to give me the velocity, how this is moving vertically. At any given time t, is going to be giving me the vertical component of the velocity vector. So at any given point, if I have a velocity vector, now that's going to give me, so if I consider this the velocity or position, I suppose, vector, and I consider the velocity vector, then I have here in this coordinate, I have y prime at that time t, not x. Notice this is going to be given, each different t is going to give me a different position. And then the horizontal component then is going to be that x prime. So that's kind of what that looks like. But now I may also consider, well, what happens or what is given that curve, the slope of the tangent line here is going to be telling me how fast is the y coordinate changing with respect to the x coordinate. So this vector right here is a vector that gives me the velocity with respect to time. But if on the other hand, I wanted the tangent line or the slope of the tangent line to this curve that is drawn, that would be dy dx. So let me erase, and I want to draw the tangent line. So now I'm going to look at this curve, not very parabola, but let's say it's a parabola. Very, very harsh turn right here, but it's okay. So if we have a parabola and I have a time t, so I'm going to be at some time t that is going to be prescribed, it's going to be fixed. Let's say t equals t naught, or equals a, because I cannot fit t naught. So at t at equals a, I do have to this curve, there is a tangent line. And that slope of that tangent line is still going to be dy dx. And what does it represent? Again, as I said, it's going to be the rate of how the y coordinate is changing with respect to the change in the x coordinate. It is not a velocity, because the velocities is going to be a vector that's going to be formed with dx dt. and dy dt. However, by the chain rule, this dx dt is still going to be dy by dt, also known as y prime, over dx by dt. Again, remember that if you were able to cancel the dt, so to speak, this guy would cancel with this. Not gonna even do it, but it will allow you to remember the formula, because if you were to cancel the dt, then that would give you just dy by dx, and that derivative then you write it as y prime of t over x prime of t. So in our particular case, the derivative, we can actually compute it, and it's going to be negative 32t over 100. And now we can try to compute at different times and figure out what our rate of change of y with respect to x be. And that's just going to be how fast, again, the y coordinate is changing with respect to a change in the x. All right, so that will give us information about the curve, not so much about the physical problem that we're talking about right now, but it definitely will tell us a lot about what the curve looks like and what the tangent lines to that curve will be looking like. All right, so now let me go ahead and show you how you would take a second derivative. So this one you can simplify. You could evaluate at different times. That's fine. Not what I'm interested in doing right now. I want to look at what happens with the second derivative. So I want to kind of abandon this example a little bit. Just leave this part. My graph is going to be gone. What would the second derivative of y with respect to x give me? The concavity of this graph. So again, I motivated it a little bit from the physics point of view, but right now we're going into a more mathematical point, in a more mathematical direction. So let me erase here. I'm going to derive the equation for your second derivative. So for the first derivative, we already have it. Let's do it for the second derivative. So using this, now let me copy dy dx. We already computed. Is going to be y prime of t with respect to, or divided by x prime of t rather. Excuse me. So now what I want to do is I'm going to take the derivative of this. This is what this one of these will look like. So you see, this right here depends on t. So when I want to take my second derivative, I'm going to be taking the derivative of this expression, which is going to be a lot like, well, taking the derivative with respect to x of this derivative that I already have. Nothing new there, not breathtaking. So far I haven't said anything exciting. However, what I want you to have in view is this right here, and that is the fact that this expression depends on t most likely. It's not going to look like a function of x. So what I will need to do is transform this derivative in terms of the derivative with respect to t. So what I'm going to do is I'm going to use my chain rule again. So I take my derivative with respect to time of dy dx, because that function right there, ooh, bad planning, I'm going to need space there, because that function right there is a function of t. So now I'm going to have to, I take the derivative with respect to t, so you're going to divide by dx dt. Or would it be dt dx, but I'm going to do the chain rule in the opposite order. So I'm going to end up dividing by dx dt. So let's go ahead and do it for this example real quick. So if we wanted to take the derivative squared, I'm going to take the derivative of this expression with respect to t. So you see this expression here is going to be the derivative that I have here. I take that derivative with respect to t, and yes, I should simplify, but for illustration purposes right now I'm not concerned about the numbers as much as I am with the idea of what we're doing. Now I'm going to divide at the end with x prime of t, which is going to be another 100 there. So x prime, another 100. The derivative here is just negative 32 over 100. So it's going to be negative 32 over 10,000. But I'm not sure if I can fit it here, so I'm going to stop right there. All right, so that's how you take your derivative. So the functions you're going to, or the formulas so to speak, that you need are going to be these for the first and second derivative. Your first derivative, and then your second derivative is going to be given by this expression here. So maybe sort of a box there. And so those are the formulas we're going to use. I'm going to do one more example, and then we're going to wrap this video up here. All right, so let's go ahead and compute the derivative of y with respect to x when the time over t is pi over 6 for this curve. So let's go ahead and try to visualize what this curve looks like. And I'm going to quickly give you an idea of it. Not going to go into too much detail. I'm going to quickly graph it. So at times equals 0, the cosine is 1, so I get 3. And the sine is 0, so I get 3, 0 at times equals 0. Pi over 6 is the one I care about. The cosine is going to be square root of 3 over 2, cosine of pi over 6. So it's going to be 3 times square root of 3 over 2. Let's put it somewhere here. I know what the graph will look like, but you'd have to plot it, of course. Then at pi over 2, for example, this term is 0, but I get a 2. So my point is going to be here, 3, 2, and then this is going to continue very, very similarly. It's going to be an ellipse. And let's go more or less symmetric. I'm not the best at drawing, so wish me luck here. So let's try to do it slowly. Not so bad so far. I shouldn't be celebrating just yet until I get the full thing drawn. Good enough for us today. And what I'm looking for is the slope of the tangent line at this point, at pi over 6 times equals pi over 6. That's the slope of the tangent line for that line. Now, remember the direction or the orientation of the curve is in this direction because I started plotting points here at 0. And by the way, to graph the whole curve, suffices to consider 0 less or equal than t, less than 2 pi. You could do this one 0, or you could choose the equal on either side. You can choose both equal, really. You would just be doubling up a point, not a big deal. But that's kind of what we're looking at. And this derivative represents the slope of that tangent line. All right, so with our formula, now derived, we can just write this as y prime over x prime. Now, y prime is the derivative of 2 times the sine, which is going to be 2 times the cosine, over the derivative of 3 cosine of t, negative 3 sine. But remember that I don't want just the derivative. I want it to evaluate it at pi over 6. So at t equals pi over 6, what do I get? Well, my derivative at that point, or at that time, at that point in time, is going to be equal to 2 times the cosine of pi over 6. Pi over 6, the cosine, remember, is square root of 3 over 2. So 2 times the square root of 3 over 2, which is just going to be square root of 3 for that. And then 3 times, I forgot my negative. Let's not forget it. I mean, the slope clearly is negative, you can see from that. So if you were to forget your negative and get a positive slope, you would know that it's wrong. And then 3 times the sine at pi over 6. From your unit circle, you know that that is going to be 1/2. And then this right here would give you a square root of 3 over 3. This 2 multiplies, or you can cancel these 2's, however you want to do it. You get negative 2 square root of 3 over 3. And that right there gives you your slope of that tangent line. And then you could even, if you were asked, you could even compute the equation of the tangent line by using the point right here. Remember, we graphed it, and it was going to be, if I remember correctly, it was 3 square root of 3 over 2. And then this was going to be 2 1/2, so it's going to be 1. You can use your point and your slope, and you can compute then the equation of the tangent line. And then you can eliminate the parameter, if you will, and graph it all in decimal sign. It would look so beautiful. It would be interesting to if I could just copy the code and put it in the description below. I'll investigate. Anyways, that's, I think, a good explanation, a good example for how to take derivatives. In the next video, we'll be doing integrals. So stay tuned, and thank you for watching, and I'll see you in the next one.